Welcome back, everybody. In this video, we're going to continue our discussion of continuous functions by giving a sequential characterization of continuity. So we've seen this kind of trick before with limits, where we talked about whether a limit existed, right, at a point A, by considering only what happened as you approached A, right, as via sequences, right, that converged to A. So we want to do the same thing here with continuity. So let's begin here with a theorem. So this will be a sequential, it's just like what's up above, sequential characterization of continuity. Okay, so let's see. I guess we need kind of all the good stuff at the beginning. So I have a function f with domain D. So say it's going to the real numbers. And I want to know whether f is continuous at some point A. So what is A going to be? Well, A just some element in the domain, right? Remember, for continuity, we don't just want a limit point of the domain, but we really want a point in the domain. So f is continuous at A. Okay, if and only if, so if and only if, well, I want to look at all of the sequences that just use elements from D. So remember, we called these D sequences. In fact, I'll use, maybe I'll introduce a little bit of notation here. So, all right, if I have some A, this is going to be a sequence. So that means it's a function from the positive integers to some codomain. Let's call it D, right? So we called this a D sequence. Okay, so A dot is a D sequence. And I'm going to write down as a shorthand, A is an element. Okay, and you could just think of this right now as the set of all D sequences. Okay, so these are all sequences whose terms are all in the set D. So if and only if I have a D sequence, A dot, such that A dot converges to this point A, then, so if this, oh, I guess I already have the if on the previous line, then, well, if I apply F to A dot, then this should converge to F of A. All right, so continuity sort of preserves convergence of sequences. Okay. Now, I just said A needs to be in D as opposed to A being a limit point of D. It could be that A is a limit point of D. So I want to add a little something extra here. So if A is a limit point of D, right? Which, by the way, even if it's in D, it doesn't have to be a limit point of D, right? So I'm assuming here that it's still in D, but if it's also a limit point of D, then F is continuous at A if and only if the limit as x approaches A of f of x is equal to f of A. All right, so let's talk about this for just a little bit before we do maybe an example of using this. So first, why am I assuming here now that A is not just in D, but is also in L of D? And the answer is, well, if A is in D, but it's not a limit point of D, well, that means that there is no sequence that converges to it, right? So it's not like super exciting that this condition holds, right? Because if there is no sequence that converges to A, then you're certainly not going to be super interested in whether or not f of any sequence that converges to A converges to f of A, right? Like that just doesn't happen. Okay. Second, if we know that A is an L of D, then we at least know that there is some D sequence, which is going to converge to A, namely A itself. All right. Okay, so that's cool. Let's see. What do we want to say? Oh, right. Yeah, F is continuous at A if and only if this is true. Well, this is how it's written all the time, but I want to show one more step, actually. All right. So let me write this actually in a slightly different order. I'm going to move the f of a down a little bit. I want to write this as f of the limit as x goes to a of x. And then I'm going to write f of a. And this shouldn't be too controversial because the limit as x approaches a of x is definitely equal to a. All right, as x gets closer to a, x gets closer to a. Yeah, not like super exciting there. The reason why I want to break it up in this way is because now what you can see is that the limit of the function is equal to the function of the limit. And that is what continuity really gets you, right? So f continuous means f, and the technical word here we like to use is commutes with the limit. Okay, that means you can apply the limit to the function or you can apply the function to the limit. And this is used all over the place in calculus where, for example, you might want to apply, I don't know, let's say a logarithm to some limit. Okay, maybe you have some function in here. And then you want to move the logarithm inside. And you say, oh, okay, fine, the limit of the log of f. Okay, well, this is only something you can do because the logarithm function is a continuous function. If you had some function with discontinuities, then this swapping, right, may not be allowed. So every time you do that swap, you need to say, oh, right, this is because my function is continuous. So that's a big deal for us. Okay, we're not going to prove this here. It's a good exercise for you. It really follows closely the proof for the sequential characterization of limits. So I'll leave this as an exercise. But I do want to do some examples where we use this. So our first example will be with the square root function. So let's say my function is the square root of x. Okay, and let's work on, say, the, I don't know, how about the non-negative reals, because our square roots don't seem to like negative numbers very much. Okay, so this is our domain D. Okay, and so first I claim f is continuous on the positive real, non-negative real numbers. Okay. All right, so how are we going to prove this? Well, what I would like to do is actually check 1 point first, right? Like this 0 point. So let's show that it's actually first just continuous at 0, and then we'll handle the positive numbers separately. So if I have some sequence, so a dot is going to be a r greater than or equal to 0 sequence, such that a dot converges to 0, then, well, what I claim, right, is that f of a dot, okay, f here is the square root function, so the square root of a dot also converges to 0, right? Well, really, I should say it converges to the square root of 0, but of course that is equal to 0. Okay, why is that true? So, in fact, all right, to show that the square root of a converges to the square root of 0, I'm going to have to show, right, that every 0 coin contains a tail of the square root of a dot. So let's start with some coin around 0, so it'll have size epsilon. And, well, I already know that a dot converges to 0. So every 0 coin is going to contain a tail of a dot. And so in particular, it'll work for not just the 0 coin of radius epsilon, but even the 0 coin of radius epsilon squared. So there exists some natural number, let me call it n, which depends, actually I'm going to say on epsilon squared here. So this is, again, some positive integer, such that when I go into the tail, then the absolute value of a sub n is less than epsilon squared. Okay, so this is all coming from the convergence of a dot to 0. Okay, we haven't checked the square root of a dot yet. Okay, but if I know that the square root, or rather the absolute value of an is bounded by epsilon squared, what does that tell me? Well, what if I want to know about the absolute value of the square root of an? Well, let's see. So first, this is going to equal, let's see, the absolute value isn't doing much to that square root now, is it? Right? The square root's returning a positive number, so that's fine. So I could drop those absolute values and just get the square root of an. On the other hand, all these an's we're getting, right, they're non-negative. So if I wanted to add some absolute values, that doesn't hurt anything, right? We know here, right, an is at least 0, so dropping these absolute values or adding them, it does nothing. Okay, but I do have this nice expression here that I already know. And of course, again, these absolute values were superfluous, but let's just keep them there for now. So I know that this is less than the square root of epsilon squared. Okay, and this is because the square root is an increasing function. Okay, so since square root is an increasing function, right? So if I put in larger inputs, I get larger outputs. And in this case, epsilon squared is a larger input. And so when I take the square root, I get a larger output. But the square root of epsilon squared is just equal to epsilon. Of course, epsilon is positive. So this tells me that the nth term of the square root sequence of a is actually bounded by epsilon. Okay, so if we like, this would imply that if I take the tail starting at this big N, that this is going to be contained in the 0 coin of radius epsilon. Okay, and so that implies that the square root of a dot is converging to 0. Okay, so far, so all this, right, all this shows square root of x is continuous at 0. Okay, that's it. So now we need all the other real or positive real numbers, right? Okay, so let's see if we can't get that going. So let's assume now that I have some non-negative sequence. So maybe I'll use a different name for it now. So how about we'll call it B. So if B is a non-negative sequence, such that B dot converges, well, I don't know, to some B which will be a positive number. Okay. Then, well, our claim is that the square root of B dot is converging to the square root of B. Okay, of course we have to justify it. So in fact, so you see the similarity here. If epsilon is greater than 0, and we're just copying it seems like, then there exists, okay, maybe we'll use a different letter now, M. And this time though, this M is actually going to depend just on the epsilon. That's fine. Okay, so it's some positive integer, and then we're going to use here that B dot, right, converges to B. So we know that if we go out far enough, right, we go into a tail of B dot, that we will get within epsilon of B. That is, a B coin will contain a tail of B dot. Okay, so there exists an M such that if little m is greater than or equal to big M, then the distance between Bn and B is less than epsilon. Okay, so consequently, if Rn is at least big N, then, okay, well, we want to say something not about Bn and B, but about the square root of Bn and the square root of B. So let's take the square root of Bn minus the square root of B. And now we play this good old trick that you might have learned even in your Calculus 1 course. So I take this expression, I'm going to multiply it top and bottom by what sometimes is called the conjugate. So I have the square root of Bn plus the square root of B over the square root of Bn plus the square root of B. Okay, now if I multiply the numerators together, I realize I'm getting this difference of squares situation. And so the numerator becomes, well, the square of the square root of Bn, which is just Bn, minus the square of the square root of B, which is just B. And then on the bottom, well, I have all this junk, square root of Bn plus the square root of B. Okay, but what do I know about Bn minus B? Well, I know the absolute value of that is less than epsilon. So if I break this up as the quotient of the absolute values, and then on the bottom, I don't even have to worry about the absolute values anymore because everything is non-negative. And so on the top, I know that this distance is less than epsilon. Okay, what about on the bottom? Well, I know that this square root of Bn is at least 0 because I'm working with a sequence of non-negative numbers. So like this even makes sense to begin with, and then it's a square root, and you take square root, it's non-negative. Fine. So if I got rid of it, then I would just have the square root of b. So this bit down here is at least as big as the square root of b. So if I replace the numerator with epsilon, it will make the fraction bigger. And if I replace the denominator with the square root of b, that makes the denominator smaller, which makes the fraction bigger. So if I do both of them, then I'm definitely on my way to making this fraction bigger. And so I've bounded the difference between the nth term of the square root of b and the square root of b by epsilon over the square root of b. And you might say, well, that's not quite over epsilon, is it? But, and this is actually not even less than or equal to, right? Because that was a strict inequality. It's not less than epsilon necessarily, but that's okay, right? Because the inspired choice theorem says you just have to get it as some positive constant times epsilon. Okay, this is a positive constant. So this is some positive number. Therefore, by the inspired choice theorem or the inch theorem, that implies that the square root of b dot converges to the square root of b. Okay, that's good enough. Okay, so that finishes the proof. Now, why did we have to break it up into these two cases? Why not do the second case, which seemed to work for all the positive integers? And the answer is, well, when we're converging to b, if b was 0, look what happens to our argument down here. At the very end, we'd have 1 over the square root of 0. And oops, a puppy just got kicked. And we don't like to do that. Okay. All right, so we're going to do one more result in this video, which is really just kind of reading the contrapositive of this sequential characterization of continuity. And then we'll do an example of it. So this is going to be called the discontinuity criterion. And frankly, I find this to be a much more effective way of using the sequential characterization of continuity, is actually to prove that something is discontinuous at a point. So here, once again, we have a function with domain D going to the real numbers R. And in this case, we're going to assume that A is, of course, in D. And even a limit point of D. Okay, so I really need to be able to find some sequence that is going to converge to A. Okay, so if A dot is a D sequence such that A dot converges to A, and such that F of A dot does not converge to F of A, then F is discontinuous at A. Okay, so this is nothing that we need to prove here, because if we head on back to our sequential characterization, we can see, right, if you have a sequence that converges to A, and then F of A dot does not converge to F of A, so this is, right, saying we have a negation of this, then we get the negation of this statement, right, the contrapositive, F is discontinuous at A. So there's nothing new in this theorem, right? However, using it is going to be very helpful. So let's do an example. We'll take one of our favorite functions, h of x, which is going to be 3 until x is equal to 7, and then once x gets past 7, it becomes 1. So visually, this should be pretty easy to detect the discontinuity. Because at 7, it just takes this massive jump down, right? Because it's a step function. Okay. Right. So visually we agree, right? Like I see the graph, yeah, there's a discontinuity there. But we can actually prove this, right, without just having to say, well, yeah, just look at the graph. There's a big jump, right? Because the definition of discontinuity didn't say if there's a jump, it's not continuous, right? It has a specific definition, right? So let's use this discontinuity criterion. So we're going to define A dot to be the sequence 7 plus 1 over n. And we see quickly, right, as n goes to infinity, 1 over n goes to 0, so this thing converges to 7. And it's converging to 7, right, though, from the positive side. Okay, so we're getting close to 7 from the right. And so what happens if I evaluate h on this sequence? Okay, I get a new sequence. It says h of, okay, 7 plus 1 over n. But for anything greater than 7, h is going to return 1. So this is a constant sequence, 1, which certainly converges to 1. But what is h of 7? H of 7 is equal to 3. Right? It comes from here. H of A converges to 1, H of 7 converges to 3, A converges to 7. Oh, it didn't work, right? We should have that H of A dot converges, right, to H of A. Well, but H of A in this case, that's H of 7 is 3. It doesn't work. So the combination of these, right, so by the discontinuity criterion, H is discontinuous at 7. Okay, so that's pretty nice. All right, in the next video, we'll write down some more properties of continuity, including the algebraic continuity theorem. We'll talk about how the composition of continuous functions are continuous, and then we'll even finish with a proof that, and maybe we'll wait one more video for that, but yeah, later video we'll prove that continuous preimages of open sets are actually open. All right, we'll see you next time.